So hello everyone, I'm Sarah, and today I'm going to talk about the solver that we specifically developed for the tracer equations that appear in the primitive equation ocean models. So first of all, a brief outline of my talk. At the beginning, I'm going to show you the tracer equation and then the ETD solver that we developed for such an equation. After that, some numerical tests that include also tests for the primitive equations, and at the end, the future work. So here we have our tracer equation discretized vertically. T indicates our tracer, K indicates the layer we're working on, and as you all know, the tracer equation can be seen as composed of four terms. First of all, we have the horizontal advection, then we have a coupling term between layers which can be properly called vertical advection, and then we have the two diffusion terms, the horizontal and the vertical one. On the right on the slide, you can see some operators that we defined for this vertical discretization. So we can see the tracer equation as written in the following way. So f of t equals to a linear operator times your tracer plus a nonlinear remainder. In all our tests, we have that the nonlinear remainder is 0. Therefore, applying an exponential integrator, we can find the exact solution. Specifically, if we apply exponential Rosenberg-Euler, we can find the exact solution up to machine precision. The problem is that in this situation, your linear operator an is the exact Jacobian, and you have to evaluate it at every time step, and this can be very expensive. So we decided to modify the linear operator in a more appropriate way considering the physics of the problem. So the transport and mixing in the vertical direction are those who cause the more restrictive requirements compared to the requirements imposed by the horizontal terms. Therefore, we said, let's split the Jacobian in two parts, a contribution given by the vertical terms and a second contribution given by the horizontal terms. At this point, you can see an x times t as a remainder, which will be linear, for example, in our test cases. At this point, you can simply neglect your remainder, and so with exponential Euler, you have a first-order accurate method. Or if you want to have more accuracy, you can add a second stage. And as Konstantin said, we can use a predictor-corrector approach for the second stage. So in our first stage, we simply have an exponential Euler method, and then to that solution, we add a correction. So we have several advantages of this method. For example, we don't need to use any phi2. We can pre-compute phi1 of delta t a and z and apply it to both stages. And then it's very easy to compute the difference that you see in the second stage, and first stage minus n, where in general with n, we indicate the contribution given by the horizontal terms only. Specifically, when you compute n first stage, you don't absolutely need to compute the full right-hand side, but just consider the horizontal terms. And this will give you an advantage from a computational point of view. Another huge advantage of this method is the structure of your linear operator. In fact, our linear operator A and Z can have a block diagonal structure. So each block represents the contribution given by an element. So in this picture, just for picture purposes, I'm showing a simplified case where we have 4 horizontal elements and 4 layers. So within each block, each row represents the contribution of a layer. So with this structure, instead of solving one large problem, you can solve many small problems. So you can apply phi1 to each diagonal block. And this structure is also very useful for parallelization purposes. Now let's move on and talk about some numerical tests. So in this first test, we have a box-shaped geometry, so a 10 meters by 10 meters box. So we have a circular velocity field, and to define that velocity field, we use two functions, phi1 and phi2, where phi1 depends only on x and phi2 depends only on z. We have 40 layers, so each block that you have on the diagonal of your linear operator will be a 40 by 40 matrix. And we decided to use three solvers. Exponential Rosenberg-Euler, because this is an easy test case, and then our splitting ETD with two stages, and finally we decided to use RK4 plus implicit Euler because we saw that at some point Ocean was using such a solver to solve the tracer equation. In particular, the vertical diffusion was treated using implicit Euler. We want to have a CFL ratio of 8, and we have it for all the three solvers. And in the table, you can see the speedups that we had. So, for example, if you compare splitting ETD two stages with RK4 plus implicit Euler, we can see that with ETD, we can get a bigger delta T, and we have a speed up of 2.87. Then, if you want to have another test case, we can move to a rectangular shaped geometry. So in this case, our X max is 40 meters. And to have a CFL ratio of 8, I modified the phi1 functions. So now the exponent is 16. And as you can see, the speed up that we have right now is very similar to what we had before. Now it's 2.74. Then some qualitative results for the primitive equations. So we decided to incorporate our tracer equation in the wider context of the primitive equations, and to solve the dynamics, we simply added a second ETD solver. So we are dealing with two tests here. The first one is the lock exchange test case, in which we have a domain where half of the water has a temperature of 5 Celsius degrees, and the remaining half has a temperature of 30 Celsius degrees. We are using z-level coordinates, so we expect the intermediate layers to have temperatures in between 5 and 30. And here you can see our result considering a horizontal viscosity of 100 compared to a result got with Ocean. I just want to point out that in our result A, we use a third order upwinding scheme for the horizontal advection. Then the second test case for the primitive equations is the internal waves. The initial condition is just a single hump of isotherms that initiates symmetric waves that propagate out from the center. If we take a DT of 300 seconds, and if we run the simulation for 200 days, here we have several results. So A shows our result, B shows the result got with Ocean, and C and D shows results that other codes got. So I'm showing C and D just for aesthetic purposes because I think it's easier to compare A with C and D than with B. And as you can see, our result is comparable with the others. So what we do now, we have to further do some tests about our splitting ETD scheme. It would be nice to have more realistic applications. We want to add multiple tracers. So we want to add also salinity and contaminants. And about contaminants, especially about, passive tracers, it would be nice to investigate spatial grid refinements. Thank you.